Hello everyone and welcome back to our discussion of elementary statistics. Today we're going to be discussing a couple new metrics that are commonly used in statistics that can sometimes be viewed as more appropriate than their arithmetic counterparts, and they're called the geometric mean and the geometric standard deviation. So what I want to do is first go over the arithmetic mean and arithmetic standard deviation, which are the common means and standard deviations that people do use in basic statistics, and then converge and segue into their geometric counterparts. So how do you calculate the arithmetic mean and standard deviations? Well, the arithmetic mean is just going to be equal to the sum of those values divided by how many values you had. Once you have that arithmetic mean, then you're going to take each of the values, subtract the mean, and then you're going to square that difference, add up all of those squared differences, divide by n minus 1, and take the square root. So that's the sample standard deviation, and keep in mind the population standard deviation divides by capital N, not n minus 1, and that's the main difference between standard deviation difference for populations and samples. So a quick calculation example, suppose you have the amount of rain that has fallen on each of the past 7 days given to be 2.1, 5.2, 3.2, 1.1, 0.3, 3.1, and 2.2 inches, right? And let's assume that somebody asks you, what is the arithmetic mean and arithmetic standard deviation of these rain values over the past 7 days? So if I were to ask you what is the average rainfall or the arithmetic mean of the rainfall values, you would obviously take the sum and divide by 7. So you would do 2.1 plus 5.2, add all the way down to 2.2, divide by 7, and you're going to find that that's approximately equal to 2.4571 inches. So on average over the past week, it rained 2.45 inches per day. Now let's go into the standard deviation calculation. So what most people do to break down that complex computation into smaller parts, we first calculate the sum of squared differences for our values. So what we're going to do is we're going to take the first value, 2.1, subtract the mean, then square it, and then take the next value, 5.2, subtract the mean and square it, and continue this all the way down to the last value, 2.2, subtract the mean, and then square it, and you're going to find that's approximately equal to 15.1771, and keep in mind this is in squared inches. And then once you have the sum of squared differences for your data set, then you can find the standard deviation for the data set by doing the square root of the sum of squared differences divided by our n minus 1, which is going to be 7 minus 1, and that's going to come out to approximately 1.5904 inches, original unit. Right, so that's how you calculate the arithmetic mean and the arithmetic standard deviation. So one question, why do we refer to it as the arithmetic mean and arithmetic standard deviation? Well, notice that in both formulas, we use addition, right? We use addition. That's a very ugly summation sign. It looks more like that. But we use addition in their calculations. That's one thing. Another reason why we view it as arithmetic is how we compare changes in our values. So for example, let's assume that on day 1, it rained 2.1 inches. And then on day 2, it rained 5.2 inches. And then on day 3, it rained 3.2 inches. So I ask you, how did the amount of rainfall change from day 1 to day 2? Usually we look at those things and subtract. So obviously this is an increase of 1.1 inches. And if we go from 5.2 down to 3.2, that's obviously going to be equal to 2.0 inches, right? So what would that be? That's that 1.1. That's going to be 3.1. Right? So that would be an arithmetic change, right? Now, do we have to analyze things in an arithmetic way? Of course not. We can obviously go where we're going, and that's going to be geometric change. Now, before we get into geometric change and some of the common scenarios where geometric change is actually more appropriate than arithmetic change, I want to sort of discuss how means and standard deviations interact, at least with respect to how some people use them. So some people will use the arithmetic mean and arithmetic standard deviation, which I'll abbreviate by SX, to construct intervals to approximate or represent sets of numbers. Most importantly, in statistics, we use x bar to estimate the population mean mu, and we use the standard deviation of our data set to construct what is called margin of errors for our quote-unquote confidence intervals. So for our particular example, what we had was x bar was equal to 2.4571, and the standard deviation was equal to 1.5904. So what we can do is build an interval around x bar that is of size twice as much as the standard deviations or some scalar multiple thereof. So we can define some interval, let's call it ik, to be equal to x bar minus k times the standard deviation, and then x bar plus k times the standard deviation, right? So it's pretty much x bar plus or minus ksx. So what exactly does this mean? So if I were to construct an interval, let's call it, for example, I1, so this would be k is equal to 1, so it's one standard deviation from our sample mean, then we're going to get I1 is approximately equal to 2.4 minus 1.5 and 2.4 plus 1.5, which is going to be approximately equal to 0.87 and then 4.05 inches. And if I were to take k is equal to 1.5, so I'll just take 1.5 multiplied by the standard deviation, add and subtract that to the mean, and then we're going to have that I 1.5 will be approximately equal to 0.55 and then 4.37, so obviously a little bit more wider. So we're trying to figure out on average how much will it rain next week, and obviously some intervals will capture more values than others, but you want to be a little bit more precise with your calculations maybe, and there's quite a few things that you could discuss here, and this eventually leads into the realm of hypothesis testing. But pretty much what we're assuming, or what we're trying to do, is trying to estimate something, for example, the population mean. That's the common one, since x bar is an estimate for the population mean. We're just trying to build intervals that kind of represent the broader picture of what's going on. Now, obviously, if I make k is equal to 50, that's 2 minus 50 or so and 2 plus 50 or so. Like, how can it rain a negative 40 inches? So obviously, there is some downsides to arithmetic intervals, which is one reason why geometric intervals enter the conversation, because sometimes arithmetically things just don't make sense. Because obviously if it rains like 50 million inches per day, going a few standard deviations from the mean, like how realistic is that, right? So this is pretty much how we build intervals from arithmetic processes, and now let's go into their geometric variations. So let's suppose that the interest rates on savings accounts are, on average, equal to the following over the past 6 months: 4.5, 4.1, 3.9, 4.2, 4.4, and 4.1% on average each month. How do interest rates work on balances for accounts usually? Well, typically interest compounds every month or every day or continuously and so on. So to give you some insight on what we have here, let's assume that you have some balance B0 at time t is equal to 0. For example, let's assume that this is equal to $500, and let's assume it has some interest rate I that compounds monthly. So obviously this 500 is going to grow into some balance. Let's assume it's called B1. So if I have this balance of 500, how do I get to B1? So B1 is obviously going to be equal to B0 plus some interest I. So obviously it's going to be some percentage of B0, so it's going to be obviously B0 times that interest rate I, and obviously we can factor out B0 out of this expression, and we're going to have 1 plus I, right? So multiplicatively, this value is just going to be equal to B0 times 1 plus I. So we go from 500 to 500 times 1 plus I, and obviously we did add some money to it, in particular B0 times BI. But from this expression, we can clearly see there are other ways to transfer from B0 to B1, because, again, B1 would just be equal to 500 times that interest rate, for example, 1 plus 0.045, and that will give you our new balance of, something more than 500, right? Let's, call it like $525. I know that's not right, but it's going to be something bigger than 500, right? So obviously we can go from B0 to B1 by adding money, in particular some percentage of the original balance, or we can find it by a multiplicative process. So one could ask the natural question, is arithmetic calculations on multiplicative processes appropriate to give non-misleading results? The answer is, for the most part, no. Obviously, you can translate them to arithmetic processes, but sometimes that transition is not very smooth. So let's see if we can construct these geometric variations of our arithmetic calculations. So let's just recall the formulas for the arithmetic formulas, right? So arithmetic means and standard deviations. So how do we calculate the arithmetic mean? So that's going to be equal to the following. So I'm going to call it x bar a to distinguish versus arithmetic versus geometric. So this is going to be equal to 1 over n times the sum from k is equal to 1 to n of our x values. So add them up, divide by how many you have. And then we have our standard deviation. So that's our second arithmetic metric. So standard deviation. So I'm going to represent by Sxa for arithmetic standard deviation. And this is going to be equal to the square root of 1 over n minus 1 times the sum from k is equal to 1 to n of xk minus x bar squared. And it's very important to note that this x bar inside is the arithmetic mean, right? So we take this value and use it in this formula. So we should be doing that also for the geometric counterpart. So now let's introduce the geometric mean. So the geometric mean, instead of adding, we're going to be, take a guess, multiplying. So the geometric mean is going to be defined as follows. So I'm going to call it x bar g, and this will be equal to the nth root of x1 times x2 all the way down to xn. So you take them, multiply all of them together and take the nth root. And some people will also write this as x1 times x2 all the way down to xn to the power of 1 divided by m. And it's very important to note that each of these values must be greater than 0 to have any calculational meaning. So if we consider our particular example of interest rates, then the geometric mean is going to be equal to the 6th root of 4.5, 4.1, all the way down to 4.1. And that's going to come out to approximately 4.1955, and the unit on those was percents. Now you might be thinking, will you get the same answer if you convert them to decimals and then calculate the geometric mean? Well, you can find that the geometric mean for this, if you convert to decimals first, would be what? So that's 0.045, and then 0.041, all the way down to 0.041. And once you take the 6th root of that, that's going to come out to approximately 0.041955, which, as you can clearly see, are the same. Right, so that's actually very, very neat. Right? Now, before I introduce the geometric standard deviation, I just want to recall some basic properties from pre-calculus or some algebra techniques. So our exponential function y equals e to the x, as we know, is just an exponential growth model. It starts very shallow and then exponentially increases. And then we have its inverse, the natural log of x, which is the compositional inverse of the exponential. So it kind of has that logarithmic growth, but it is pretty much just a mirror image of our exponential function about the line where is equal to x, right? So you just flip them over about that green curve and you get that orange curve, which we call the natural log. And the compositional connection between these are going to be the following. So the natural log of e to the x is the same as x, And we also have that e to the power of the natural log of x also is equal to x, right? So that's the inverse property between e to the x and natural log of x. And some important properties for the natural log is that the natural log of a to the b would be equal to b times the natural log of a. Another property that's very useful is that the natural log of x times y will be equal to the natural log of x plus the natural log of y. And a generalization of this one, instead of two numbers multiplied, we can have n numbers multiplied, is that the sum of natural logs, so the sum from k is equal to 1 to n, of the natural log of xk is actually just equal to the natural log of the product from k is equal to 1 to n of our xk values. Right, so this is the sum of logs is equal to log of products, right? So the sum of the log of the numbers equals the log of the product of the numbers, right? And that's going to be a very important calculation once we enter the realm of geometric standard deviations. But before we get into that, I just want to note you can actually calculate the geometric mean using this clever trick. Now, obviously you wouldn't because the original definition is much more nicer, but you'll see where these things actually start connect to each other. So we have that the geometric mean, again, was equal to just the product from k is equal to 1 to n of each of our xk values to the power of 1 over n. And what I can do is I can use that compositional relationship between e and natural log, and I can just write this as e to the natural log of something, where that's just the product of our xk values to the power of 1 over n. But what is this number? Well, this number can come down by properties of log. So we can write this as e to the 1 over m times the log of the product of xk. And what is the log of the product? Well, that's just equal to the sum of the logs. So we can actually write this instead as e to the 1 over n times the sum of the log of the x values. And if you actually look at this exponent very carefully, that's just the natural log of x1 plus the natural log of x2 all the way down to the natural log of xn, all divided by n. You might think, does this exponent kind of look like an arithmetic mean? It actually is, right? But instead of the arithmetic mean of the values, is the arithmetic mean of the natural log of the values. So we get a very intimate connection between arithmetic and geometric processes, in particular that the geometric mean of values is equal to e of the natural log of the x, the average of that, under your arithmetic processes. Right, so the geometric mean is just equal to e to the power of the arithmetic mean of the log values. If you're using R for any computational calculations, then you can actually use this code. So x bar g will just be equal to e to the power, which is exp, and then the mean of the log of your sample data set values s, right? So x bar g, geometric mean, is just e to the power of the mean of the log of the values, right? And that's a very, very beautiful connection. Now, would you ever use this in practice? Probably not, unless you're in theoretical mathematics. But this connection between them actually gives rise and a reasonable way to define geometric standard deviations, right? Now let's get into that. So as already mentioned, this calculation for the geometric mean of e to the power of the arithmetic mean of the log of the values obviously is not very useful outside of the theoretical realm, because most people will just take each of the values, multiply them together, and then take the nth root of that product. But of course, why do we care? Because it gives us a nice way to define the arithmetic standard deviation of a set of numbers. So using this same exact idea, so the geometric standard deviation will be equal to e to the power of something. So what we're going to do is we're going to define it as e to the power of the square root of 1 over n instead of 1 over n minus 1 of the sum from k is equal to 1 to n. So it's almost like the arithmetic standard deviation of the natural log of the values. So we're going to do the natural log of the values minus the natural log of the geometric mean and square that difference. Right? Now, again, how do you calculate this? So keep in mind, let's bring back our data set. So our data set S was equal to 4.5, 4.1, 3.9, 4.2, 4.4, and 4.1%. And we already know it doesn't really matter if we convert that to decimals or keep it in percent forms, because we will still get the same exact answer. And remember that the geometric mean for these was approximately equal to 4.1955%, right? So let's just keep things in the original unit, and also the same for the geometric mean. So how would I calculate the geometric standard deviation? So the geometric standard deviation will be equal to e to the power, which I'll just write as exp for now because it's a lot more easier to write instead of that complicated exponent. And then we're going to have 1 divided by 6, and then we're going to have a bunch of addition. So what we're going to do is we're going to do the natural log of 4.5 minus the natural log of 4.1955. We're going to take that difference and square it, and we're going to do that all the way down to the last value, 4.1. It's natural log. Let's not forget our logs. So the log of 4.1 minus the log of our geometric mean, 4.1955, and then square that, add, and then exponentiate that with a base of e. And once you do that calculation, and you do not round very heavily in the middle, what you're going to get is a arithmetic standard deviation of approximately, what is this going to come out to? Give me just a moment. That will come out to approximately 1.0023. Now, a very interesting question. What is the unit on these particular objects? Well, you should be able to verify that this is going to be equal to the original unit that the data set was in. But what about this particular unit? This is a very, very interesting question, and I'll leave this for you just for the time moment to think about. Right? But the answer is actually geometric standard deviations do not have any unit at all. Right? It's very strange at first. But if you know a couple mathematical properties, hint, the natural log of a minus the natural log of b will actually be equal to the natural log of a over b. And I'll give you some moment to think about that if you want to sort of have a nice little mathematical puzzle to explore on your own. Right? So we clearly see from these definitions there is a big connection between arithmetic and geometric processes, at least in terms of means and standard deviations for metrics. So we have that the geometric mean is equal to exp of the natural log of x bar under arithmetic calculations, and geometric standard deviations is equal to e to the power of the standard deviation of the natural log values under arithmetic calculations. So we get these two very important calculations or connections, and this will be in the original unit, and this will be in no unit at all. So how about building intervals for estimation under geometric metrics? So recall, for our arithmetic processes, our interval was equal to x bar a minus k sxa, and x bar a plus k sxa. So in arithmetic processes, what do? We add and subtract a scalar multiple of our standard deviation, right? And this is for arithmetic. So this is for arithmetic. So what about for geometric? You want to take a guess? So the geometric will be equal to x bar g. So instead of subtraction and addition, we're going to do division and multiplication. So what we're going to do is we're going to take our standard deviation, geometric, and we're going to raise that to the power of k and then divide. And then we're going to take our geometric standard deviation and multiply by the geometric standard deviation and raise that to the power of k. Right? So this is for geometric metrics. Right? So those are the interval ways to construct intervals for estimation under arithmetic and geometric metrics. So if we use the numbers from our example, right? So recall some of those numbers. So our geometric mean was approximately equal to 4.1955%, and our geometric standard deviation was approximately equal to 1.0023. And keep in mind there's no unit on that particular object. So if I do, for example, k is equal to 2, and I calculate a geometric interval for that, that's going to be equal to this geometric mean divided by geometric standard deviation squared. and then geometric mean times standard deviation squared. And that's going to give you approximately 4.17 to 4.21%. So that's two geometric means from the two geometric standard deviations from the geometric mean. And if we do k is equal to 3.4, then I geometric 3.4 will be equal to, so we're going to take our geometric mean divided by our geometric standard deviation to the power of 3.4, and then our geometric mean times our geometric standard deviation to the power of 3.4, and that's going to give you approximately 4.16 to 4.23, obviously, again, wider in percent. Okay, right, so what does that mean? So that's 3.4 geometric standard deviations from the geometric mean. Right? So now we've introduced, these two geometric metrics that actually have quite a lot of properties, and finance is one of the many applicational worlds where geometric processes are actually a little bit more trustworthy or reliable or meaningful compared to their arithmetic counterparts. So a natural question, because if you remember, we actually introduced several different metrics. We have mean, median, mode, standard deviations, sum of absolute differences, variations, coefficients of variations, percentiles, and so on. So are there other geometric equivalents to the other arithmetic? That doesn't look like arithmetic, does it? To the other arithmetic metrics? The answer is yes. I'll actually introduce you to one because I think it's very, very basic to work with, and that's the geometric z-score. Right, so the geometric z-score. So the geometric z-score compared to the arithmetic z-score. And the geometric z-score is defined to be equal to the natural log of x minus the natural log of the geometric mean, all divided by the natural log of the geometric standard deviation. So compared to the original normal arithmetic z-score, which tells you how many arithmetic standard deviations are you from the arithmetic mean, this answers pretty much the parallel analogous question: how many arithmetic standard deviations are you from the how many geometric standard deviations are you from the geometric mean for your data set? Right, and obviously there are some parallels for other metrics as well that we won't get into, but this is just a brief glimpse into the geometric world. So I hope you enjoyed this video, and I'll see you in the next one. Take care.